All right, great. So I'll be talking this morning about using QMC Pack to do calculations of condensed matter. And particularly this first lecture will be focused on the solid state. So the questions that hopefully will be answered by the time we finish this, you should know how calculations of solids are different from calculations from isolated molecules, what sort of theoretical considerations you need to worry about. You should know about finite size effects and how we tend to mitigate them. And it'll be a discussion about the current best practices for using pseudopotentials for the condensed phase, which has one slight additional requirement, at least as we use them in QMC Pack. So the first is going to be computing the interaction energy. So David mentioned this in the first day at least, but we're going to be using a finite size simulation, obviously, and we'd like to get properties of solids in the thermodynamic limit, right? So bulk material. So one way you can imagine doing this is just doing calculations of ever larger clusters, but you basically have a hard time getting around surface effects. So what we do is we use periodic boundary conditions to speed up that convergence quite a lot. Now, in moving to periodic boundary conditions, the Coulomb potential is now not just between two electrons, let's say that you're moving around, but it's also between all the periodic copies. You want to have the full solid included in the calculation. And the canonical way of doing this is with Ewald sums. So we do a periodic interaction that's found by summing the interaction between the particle that you're interested in, let's say, and this infinite periodic array of charges. Now, with a 1 over r sort of interaction, we know this is conditionally convergent. This is sort of basic solid state. And the standard procedure that we use for doing this interaction is the Ewald sum. So the way this works, we have this infinite summation. You've got particle at r prime and other particle at r. And now we're going to sum over all of our lattice vectors in the three directions, right? So what we do is we use the fact that things are linear, and we screen that charge with some sort of Gaussian, right? And now we have something that converges nice and quickly in real space, right? Everything's going to decay. And then we put the other piece in reciprocal space, where things converge relatively quickly. Now in QMC Pack, we actually use an optimized form of this potential, and this is, I think, first detailed here in this 1995 article. So this takes advantage of the fact that there's nothing magical about using a Gaussian to screen your charge. So instead of screening this delta function charge that we're moving around, we're going to explore the freedom using some sort of spline to speed up the convergence of both the reciprocal space and the real space sums. So the error in the method actually goes as your cutoff values RC and KC. And you'll notice if you look in a QMC Pack input file for a solid state calculation, that there's this value LR dim cutoff, and that's the product of these two. So the larger that number is, the more accurate your calculation of this interaction will be. And please feel free at any point to stop me. I very much prefer an interactive style of lecture. So why do we care about this? The real space part of the Ewald sum, has the order of hundreds to maybe thousands of terms for a typical calculation, as does the reciprocal space part. And if you've been sort of following trends in computer science, they're telling us that we should worry about data movement and that floating point calculations are basically free. So why do we really care about this? And the answer is sort of how many times do you evaluate the interaction between point charges in a typical, say, DMC or VMC calculation? It's really the same. So just sort of back of the envelope, for each Monte Carlo sweep, right? So we're going to do single particle moves. Let's say we have in the order of 100 electrons for a reasonable cell. We've got 100 electrons. We have to evaluate the interaction with all other 100 electrons every time we do this, right? We'll have on the order of 1,000 walkers, say now, sometimes more, sometimes less. And we generally move on the order of 1,000 times each walker, so 1,000 generations of thing. And pretty quickly, we're getting to rather large numbers. So I've never seen the calculation yet, certainly with the QMC Pack method, where this dominates your computational time. But you can imagine that, especially for sort of smaller calculations, you want to be careful. And that's one reason we've done it. So An advantage that QMC Pack has over some other techniques is that we can use arbitrary boundary conditions. So everything I was saying before is ostensibly for purely periodic boundary conditions in all three directions. But we can actually mix the boundary conditions. So for example, you can say we want a periodic interaction in two directions. Let's say I'm doing a 2D material, graphene or something like this, and I'd like to have vacuum. So in your DFT calculation with plane waves, you probably just have to have a really big box, right? But in QMC Pack, once you've got that wave function, and representing that can pose some problems, but once you have that, you can just turn off the interaction in the z direction, or the periodic interaction in the z direction, and then you get the convergence right off the bat. So as I say, this is implemented and it maps directly onto the input file, and we'll have an example in the lab later today of that. So this is the reference for the optimized Ewald. Mainly this is if you want to read more into this later. And then there's a great review article. It's getting a little bit old. There are actually some newer ones, but I do always keep going back to this one. Anytime I want to look up something about doing QMC calculations on the solid state, this is a great place to start. So everyone happy with the material so far? Great. So now we'll look at basis sets for representing the wave function. So as we've seen and gone quite far beyond in yesterday's lecture, the simplest and probably most common form of the wave function for QMC calculations is this Slater-Jastrow form. Now in the solid state, it's actually considerably harder to go past this. There are some extensions, but this is going to be our big workhorse. So you get your Slater determinant from some method, and then the Jastrow factors are going to be determined through optimization. So what that looks like, with the exception of things like the cusp condition, which we know. And then the single particle orbitals will generally come from somewhere else. So what do those look like? So the most common source that we have for these single particle orbitals that'll go into our Slater determinant is to use a density functional theory code. And we've typically worked in a plane wave representation. We'll go in a bit more into this, but basically the size of your basis doesn't matter too much for QMC as long as you can store it in memory and evaluate it quickly. And we've got some good tricks for plane wave, and as you know, we can converge it very easily, right? Just increase the cutoff, increase the spacing, and you get the converged thing. So we don't actually use plane waves directly in QMC Pack. I think it's maybe buried in the functionality if you really feel masochistic. But the reason is that every time you are going to imagine moving an electron to another place, now we have to evaluate this entire sum, right? So every basis element has to, in principle, be evaluated for every single particle move. And you can see that this gets expensive very quickly. So what we do use is a real space spline basis. So this is 3D Bsplines. And the advantage of these, well, there are several, but one of them is that they're systematically convergible. But at any point in real space, in 3 dimensions, there are only 64 of these that are non-zero, right? So again, as I was saying, I can crank up my plane wave cutoff as high as I want. I can have a very finely resolved mesh in real space for these things. And I've got a constant cost to calculate. And from Zhang Nim's talk yesterday, you can see that we've spent quite a lot of effort in optimizing this, so it works well with modern computers. Another nice thing is that you do your plane wave calculation, and then you can adjust the spacing of your grid very easily with a Fourier transform trick. So you don't have to keep repeating your DFT calculation. Just do something that's converged, and then you can choose your coarseness, let's say, of your B-spline. Now, this isn't free, of course. So it's extremely efficient in terms of lookup, right? You can just calculate where you're going in this real space table and then grab your coefficients. But it can be somewhat inefficient in terms of the total memory used. So for instance, Gaussian basis sets being localized and small in support typically store a lot less data. So there are some tricks that we do, right? So some reasons that this may be inefficient in storage is that all wave functions could be small in a region of space. So imagine this graphene example that I was giving you before. Very far away from the sheet, the wave function is going to be essentially zero, right? Wave functions are going to vary most rapidly near the nucleus, as a rule. So typically, the spacing of your basis is going to be determined by what's going on right near the nucleus, and you don't need that sort of resolution in the interstitial regions. And you could have the case, imagine we do some sort of transformation, let's say to Wannier functions, where a given single particle wave function might be large near one atom, let's say, and basically zero elsewhere. So again, if we're storing each single particle wave function as a 3D grid everywhere on these Bsplines, that's somewhat inefficient. Now, QMC Pack has tricks to address several of these issues. So the first is this case of, let's say, graphene, where I've got something like vacuum included in my calculations. So the way we do this and maintain sort of an efficient usage of memory and vectorization and all of this is we'll generate one coarse B-spline table that's valid everywhere. So if some electron happens to walk really far away for whatever reason, you still got it represented. You don't have an actual zero, which can cause problems. And then near all of the atoms, you'll have a much finer table. So what the code's using right now is a factor of 2 smaller spacing between the grid points, so 8 times bigger, but in a limited region. So this, again, it preserves the efficient streaming of data from memory to CPU for vectorization. And you can see you can get pretty quick or pretty large reductions in memory from this. So in the case just half of my cell is vacuum, I can get the memory reduced by 40% or so. So there's another trick that we have in the case where you have, say, very hard pseudopotentials and you need a very fine spline spacing near all of the nuclei. So this requires you have a high plane wave cutoff, let's say in your DFT calculation. And the trick that we're going to use is inspired by augmented plane waves. So the idea is that around each nucleus, the wave functions, you can see here, these this is your regular grid that we would be using. But we can actually represent the wave function as some sort of set of radial functions times YLM. We know that's completely general. And then in the interstitials, we keep this B-spline table, but much coarser. So again, it's nice. We can actually do some tricks evaluating the non-local pseudopotential that keep things very quickly, right? Because we're at the same radial distance when we evaluate that. And we have this regular B-spline table elsewhere. So again, we get an efficient use of our memory, of our vector units. And this often can reduce your memory by a factor of 4 to 8 if you have hard pseudopotentials. Now, a capability that we don't have, at least easily implemented right now, is the ability to localize wave functions and truncate orbitals. So there's a paper actually dating back to 2001 where they noticed that in the case of insulators, you can construct strictly localized Wannier functions for your wave function. And that means that when I want to evaluate the total antisymmetric wave function, some things will be strictly zero, right? And in fact, you can work out that for an insulator, the number of orbitals you have to evaluate doesn't change with system size. So if you're after sort of cohesive energy sort of properties, you can actually get a linear scaling quantum Monte Carlo method in this way. Now, I think there may have at one point been a capability kind of like this in QMC Pack. And the reason that we don't typically do this is because it requires a very random memory access. So it's something that we kind of have in our back pocket. Now, in the case of purely periodic calculations, so you want to calculate the energy or some property of a crystalline solid, there's an additional trick that we do use quite a lot. So when you've got a lot of symmetry. For orbitals coming from a mean field theory, you can use Blochs theorem, right? So this means that I can calculate my wave functions in a primitive cell at a variety of k points, and then I can actually do an expanded zone scheme where I can use those wave functions to handle the many-body wave function in the full supercell. So the nice thing about this is it reduces your memory usage by a factor of n, where n is the number of copies of your primitive cell. And so this is implemented and it's used quite extensively. So QMC Pack was also designed sort of from the ground up to make things like this work. So Zhangnim described this a little bit in her talk yesterday. But the way the code is structured is that on a given node of your supercomputer, which generally has kind of on the order of tens of cores these days, we have a single, say, MPI process, or maybe you'll do an MPI process per NUMA or something like this. And each one of those will have the trial wave function, or the antisymmetric part of the trial wave function. But you don't have a copy of it per core, like you might in an MPI-only code. And for these solid-state calculations, that often makes all the difference in being able to run or not. So typical wave functions, especially if you want to have disorder, can be on the order of tens of gigabytes. Right? So you'll want to keep track of the combination of MPI and OpenMP. If you aren't using, say, OpenMP too much, you get a lot more of this large static data when you're running your calculation. And so it reduces the memory by nearly a factor of the number of cores per node. Of course, right now we have to have at least one walker per core. If you have a lot of electrons, the memory usage for them grows as the number of electrons squared. So eventually those can dominate. But for most of the calculations you're likely to do, at least in the near term, it's the wave function that's going to dominate your memory usage. All right, so here's a series of references for this. For the splines, there's an early paper, Alfei and Gillen. There have been a number of subsequent papers you can look up as well. Here's the linear scaling. The GPU paper that shows the implementation of QMC Pack on GPUs actually contains the details of that trick for using an APW representation of the wave function. And then there's a paper on the hybrid parallelization in QMC Pack. If you're like me and your institution doesn't have great journal access, this paper can be a little bit difficult to come by. So I think David's website actually has a preprint copy that I would encourage you to go to. So everyone's probably asleep by now. Let's ask a question. When I'm doing a calculation and I double the size of my supercell, just naively, I'm not using Blochs theorem or any tricks, how does the memory that I need to store that wave function change? I guess could you hit your microphone, please?
Double it in X, Y, and Z, all of them, or just one coordinate?
Just one coordinate, twice as many atoms in your supercell. How much more memory should you expect to use? So did I hear twice as much? So you've got twice as many electrons, so double the number of bands, right? So you've got a factor of 2 right there. But then if you're using a plane wave basis set or Bsplines, something like this, you've got twice as many basis functions as well. So you'll expect n squared, or sorry, a factor of 4, right, increase in the amount of memory you need to store the wave function. All right, now onto the reason that these calculations get very expensive, and that's finite size effects and this applies actually to all many-body calculations in solids. So we're using periodic boundary conditions, as I mentioned. Periodic boundary conditions imply that the Hamiltonian isn't going to be changed whenever you have a discrete translation of the system. So this should sound a lot like Bloch's theorem from your solid state course. But the wave functions can pick up an arbitrary phase, right? So everything that isn't observable is only going to depend on the wave function squared. And in order to sort of get your converged answer, you're going to want to integrate over all of these boundary conditions. So in DFT, or a single particle theory, this is often called K-points. We like to think about it in terms of the boundary conditions of the wave function in quantum Monte Carlo, so we'll typically use the term twist averaging to cover this. So how does this work? So we're going to be averaging over all of these boundary conditions. And so basically choosing the phase of the boundary conditions, right, that thing is equivalent to applying a magnetic field to your system. So you can imagine just changing your Hamiltonian. So now in this case, we're going to factorize the wave function into real and imaginary parts. Okay? Now the problem at least conceptually, that should come up. We're talking about fermions. We're applying the fixed node approximation for everything we're going to be doing here. And if I have a complex wave function, it's a little less obvious. Okay, what are the zeros in my wave function? How do I constrain the boundary conditions? So what we do is apply what's called the fixed phase approximation. So it says I'm going to get my phase from elsewhere, typically my DFT calculation. And then we're going to solve the real part of the equations using exactly what looks like fixed node DMC. And it turns out that the error in doing that looks almost exactly like the real space fixed node DMC. So you don't have sort of at gamma where everything can be real, one kind of error, and then away from gamma, something different. Now there is a relationship, and I've sort of been making this comparison throughout the talk, between the one-body finite size effect. So this is due to the fact that any single particle that I move across the boundary conditions can pick up a phase, and integration over k points in DFT. So in the case that you sort of have the same kind of Fermi liquid, they should be almost exactly the same. So in some cases, what you can do, let's say you don't want to run a lot of k points for some reason, is that you can do a converged DFT calculation with a very, very fine grid. Then do the calculation with the same k-point grid that you're likely to do in your supercell in DMC, and then use that correction. So DMC calculations at different twists are statistically independent. So generally, you're not going to need to do something like this. It's efficient to do lots of different twists. Now, if you go too far down this, you still have to equilibrate all of these calculations separately. So you can actually have your calculation be dominated by the equilibration phase. But normally, you don't need to worry about this too much. This is a little bit hard to see. I hope those of you that are following along the PDF can see this graph. But if you look in the literature at papers doing calculations on solid, people have often sort of constrained themselves to using between 1 and 8 twists. And that's because then you didn't have to update your code to use complex wave functions at all. You can always do a trick to make things real with periodic or anti-periodic boundary conditions, which is why you can get to 8. And this is an example, I think, in this case that I was doing aluminum, where 3 by 3 by 3, 4 by 4, so on and so forth. You can see that there's actually non-trivial changes in the energy from doing your twist averaging better. Now, and I'll show some more examples from this paper. It's actually not necessary to do all 343 of your twists. Let's say if you want a 7-cubed k-point grid in the case that you have a highly symmetric cell. So any k-points that are related by symmetry, just like in a DFT calculation, actually should give you the same result. So if you identify them and have the proper factors, you can reduce this quite massively. Okay, now this is a way in which the finite size effect from doing a small cell in diffusion Monte Carlo or a mini-body method is going to be different than what you're used to in DFT. Now, it turns out in DFT there are no two-body finite size effects, basically because all the functionals refer back to, almost all of the functionals refer back to David Sepperly's work, where he calculated the correlation energy extrapolating to the thermodynamic limit. So that's already done for you. But when we're doing diffusion Monte Carlo directly, that's not the case. So the reason for these interactions is that we're now calculating, let's say, the interaction between our particle that we're moving around, not just its nearby electron, but because of periodic boundary conditions, it's an infinite repeated grid of all the image electrons. That's not physical. Those should be decorrelated. And this introduces a finite size effect in your calculation. So for supercells of the same aspect ratio, that means I take a cube, make it larger, right? The error in the energy per particle from this spurious two-body finite size effect goes as 1 over n. It's a number of particles. So it's pretty slow to converge. And it's painful, right? So extrapolation to the infinite system, when you have error bars, you can't just do 2 calculations. You need to do at least 3 points. And when your method scales for large systems, as ours does, as n cubed, that's going to get very, very costly. So we'd like to get around this whenever possible. And for this reason, there actually has been quite a lot of work on finite size correction schemes. So the idea here is I'd like to do my calculations in a relatively small supercell and then have some analytical method that's going to tell me what would have happened if I had done the calculation in an infinitely large cell. Now, at the moment, These methods are pretty much limited. This slide's actually a little bit out of date. Pretty much limited to total energies. So if you want another property of your system, in general, you're going to have to think about doing the scaling yourself. Now, one example that I know of, if you want the momentum distribution, there's actually been some really nice work on getting the finite size effects done in a manner more akin to this. So that said, let's say that we're interested right now in total energies and we want to know what the thermodynamic limit. There are three methods that are in wide use now for doing this. The first takes advantage of an approximate DFT functional. So this is very cheap, and I'll show you how that works. Another one replaces the Coulomb interaction in your system with another interaction that's designed to minimize these spurious effects. And then finally, we actually know analytically something about the long-range behavior of the wave function, and we can use that to correct our total energy. So first, this approximate density functional that I mentioned. So in 2008, there was a paper by Cui, Zhang, and Krakauer, and they noticed what I just said. Most of these density functionals that we're using in solid-state calculations are based on the exchange and correlation from the electron gas extrapolated to the thermodynamic limit. Well, that's a choice, right? But what if we want to know what those finite size errors were? We can actually either mine existing calculations or do some more calculations on the electron gas at finite numbers of particles, explicitly including this two-body finite size effect. We create a DFT functional that's parameterized to that. So in this case, an LDA, because that's the easiest thing to do. And then we run that functional on our problem, right? So we're going to get directly the exchange and correlation error. And even slightly better than this, we're going to get changes to the charge density that come from this intentional finite size effect that we're putting in. And now we just compare the result of that calculation in DFT to the standard calculation that you run that's free of them. And that gives you a good idea of your two-body finite size effects. Now, a word of warning. The best chance for accuracy using this method, you can think, is when the LDA, which is what this is based on, is already doing a reasonably good job. Now, it doesn't have to be perfect, but you want sort of the long-range behavior to be similar. I'd worry about it, for instance, if LDA was predicting a metal when your system was actually insulating. So in some cases, it's not maybe the most exciting place to spend millions of CPU hours if this is going to work well. So there are reasons for other methods. Although I would recommend everyone always start here. It's very, very cheap. So if you have an idea, say you do a couple cells and it's working well, this is going to be your quickest answer. And it's going to make your program manager happy for not using all your allocation. So the next finite size correction that is actually relatively cheap as well is to say, okay, the Coulomb interaction has this problem, right? I've got these spurious interactions with this periodic grid of electrons that are caused by my boundary conditions. But for the Hartree part, so this is the direct charge part, I can analytically figure out what this error should look like. So the way this interaction works, it replaces your sort of Coulomb interaction with a screen sort of interaction that takes into account the errors that come from the Hartree piece of this two-body finite size effect. So it requires previous knowledge of the charge density. So again, we're typically going to use DFT to get that. DFT does a reasonably good job for most systems of the charge density. And a nice feature of it is that the cost of evaluating the interaction doesn't grow with the system size. So it's cheap to do even for larger systems. It can be quite accurate, but, and this was pointed out in a series of papers, it does miss one part of the two-body finite size effect. It only takes into account the two-body finite size effects coming from this potential part of the term. There's actually something from the kinetic piece. So you can get to this by knowing something about the long-range behavior of the wave function of the interaction. So a way to do this is to say I can actually write my interaction energy in this case, as an integral over the structure factor. So this is the diagonal part of the density matrix. All right? And in principle, we'd like to integrate everything. And this is in terms of distance, let's say, between particles, or the reciprocal version of that. So now in a finite size simulation cell, we actually don't get to do this integral, right? We're doing some summation over all the k vectors that are commensurate with the supercell that we have available to you. So there's a discretization error that happens when we're looking at this, but we would like to have this. And that's kind of the origin of the finite size effect for the potential energy. Now, what to do about this? So the dominant part of the error actually comes in the small k limit, right? This is your long-range limit, so that shouldn't be too surprising. And for k goes to 0, there are actually analytic forms that are known. So for instance, the RPA, basically it's the plasmon that's going to give you this behavior. So what you can do is you can calculate your structure factor. Now, if you do this naively in say, diffusion Monte Carlo, you get a mixed estimator, so be careful about that. You'd like to get the pure estimator of the charge density. And then fit that. Now, something that was noticed in this 2006 PRL is that when you change the size of the system, your structure factor typically doesn't change. It's just where you can evaluate it that changes. So you can see all these different points on these curves. This is the structure factor, and this is the Jastrow factor, which I'll get to in a minute. But you can see that they all fall in the same curve. So this means when you do a calculation for a fairly small cell, you can go ahead and use that information to figure out what's going on in the thermodynamic limit. It's not going to change as things get larger. Now, there's a similar formula for the kinetic energy. There's a finite size there. And there you need to know the long-range sort of behavior of the wave function as two particles get far apart from one another. And again, this is something that we can get from our calculations. So if you do that, you get a nice analytic answer for your finite size effects. So these are the general references. For twist averaging, we've got a couple papers for the fixed phase approximation. So basically how we can do fixed node when the wave function is complex. And for twist averaging itself, this approximate functional was a paper in 2008. There's actually an update that extends that to LSDA. So if you have systems where spin is important. Several papers on the model interaction, and then on the fit to the long-range behavior. This 2006 paper, and then there's a new one that's on the archive that sort of updates that. It actually also talks about grand canonical twist averaging. So what I said before is we can change the boundary conditions, but we're assuming that the number of electrons doesn't change. Well, in DFT, you know that, say, when you get to the Fermi surface, there would be fewer electrons for a given K point. So you can actually extend your method to deal with that nicely. So far so good, or do we have any questions? Yes, please.
So for the twist, how is the twist implemented in QMC Pack? You just add an arbitrary phase?
So the phase is going to come from your DFT wave function.
Okay.
In the fixed phase approximation.
But how do you generate different twists?
Oh, so you want to actually just run a calculation at a different twist. So you just use, say in your periodic DFT calculation, you use the K point that's equivalent to that twist, right? And then that wave function has the information that you need.
Nice.
And tools like Nexus are set up to do this for you naturally. So you just basically have to specify, this is the set of twists that I want to run in my final calculation, and then Nexus will figure out what K points that you need in your DFT.
And my second question is for the two-body finite size effect.
Yes.
Does DFT have that kind of problem?
No.
It's because we didn't move electrons in DFT, so we don't have this kind of...
So in DFT, the finite size effects are actually taken care of in the exchange correlation functional. So no matter what size of calculation you're doing in DFT, you're using the exchange correlation that's already been extrapolated to the thermodynamic limit.
Okay.
So all you have to worry about are what looks like the one-body finite size effects. With the exception of, let's say you use the KZK functional, right? That explicitly is designed to include finite size effects. So don't use that for production DFT unless you're trying to correct something. All right. If nothing else, we'll move on. So we've kind of covered this, but would anyone like to say how finite size effects in diffusion Monte Carlo or a mini-body method are different from finite size effects in DFT? Everyone's asleep. Okay, so the principal difference is just what we said. There are going to be two-body finite size effects in your mini-body calculation that are typically not present in your DFT. Okay, now on to a pretty practical topic, and that's pseudopotentials. So diffusion Monte Carlo, as we've said kind of over and over, for large systems, the cost is going to scale cubically with the number of electrons that you're looking at, right? Now, unfortunately, scaling with atomic number for your elements is considerably worse than this. So as I go down the periodic table, what happens? So first, there's an n-cubed factor due to the number of electrons increasing as z, right? Then we've got an energy scale that's increasing, right? Say the 1s electron is going to be much more energetic for tantalum than it is for hydrogen, right? And you can think that the approximate error in your trial wave functions, in practice this is more or less true, is sort of not changing. You're not getting a much better wave function for a heavier element, so your variance increases, right? Your importance sampling isn't magically getting better as z gets better. That means that your time step has to be reduced as well, and you have to run longer. So estimates of this cost are that QMC scales as z to the 5.5 or z to the 6.5. Okay, we're in couple cluster territory. We've got to do something about this, right? So what we do is what's done in many methods, including quantum chemistry often, and that is we use pseudopotentials. So the obvious solution to the problem is to say, look, the 1s electron in tantalum is not doing anything unless I'm doing something crazy, right? Instead of explicitly simulating that, I should have some sort of effective potential that everybody else is feeling due to these electrons that are chemically inert. Now, the theory of pseudopotentials is quite old, and what people have found out is that a non-local object works much better than a purely local one. So this means that the spherically symmetric, the s equals 0, or L equals 0 electrons feel a slightly different potential than do L equals 1, L equals 2, and so on and so forth. So if you think that one of the main jobs of these objects is to make sure you remain antisymmetric to your core states, that makes sense. Now the question is, how do we introduce a non-local potential, at least efficiently, into diffusion Monte Carlo? Now this was first figured out, I think, around 1991, detailed in this paper. And for a non-local potential, what they do is they use the effective interaction for the non-local channels of that potential on the trial wave function that you're feeding in. So this is called the locality approximation. So you basically have a method for, once you know the non-local components, let's say, which you do by an integration in your Monte Carlo over the sphere, you then just apply an effective interaction that assumes your trial wave function was right. Now this, sort of in the spirit of the zero variance principle, this will become exact when your trial wave function is exact. However, it's not variational. So this can actually mean that your DMC energy will be below the true energy for this given Hamiltonian. And the approximation is only applied to the non-local parts of the potential. So this means if you happen to make them small or they go to 0 for whatever reason, you won't have a locality error. So a little bit more on the form of the pseudopotentials that we can handle. So in QMC Pack, what we're evaluating is actually a semi-local pseudopotential. So around each ion, you're going to project onto the given angular momentum channel, and then he'll apply this locality form. Now, if I go to my favorite plane wave DFT code, okay, they've probably moved on from this form of pseudopotential, the ultrasoft or something like that, but they'll probably have something like the Kleiman-Bylander form implemented. So this is really efficient in DFT because instead of projecting out the angular momentum components, you project out something that looks like, say, the atomic states, and then you apply your potential to that. So it's just a dot product instead of an integration over all space. Now, implementing a projector like that in diffusion Monte Carlo is painful, and it's not generally done. So we actually employ this semi-local form in our calculation. And that means that, for instance, if you have ghost states in your potential, which is something that comes up in Kleiman-Bylander, that can screw up the wave function, say, from quantum espresso that you're handing into DMC. So you need to be careful here. Also means techniques like nonlinear core correction aren't available at the moment. So what I told you about was the locality approximation that is great in the limit that you have a really good wave function, but it's non-variational. And so it was actually noticed that you can restore this variational principle. There's a 2006 paper on this. So you introduce a discrete Green's function, and then you sample that. So it's colloquially known as Tmoves for the sort of transfer, this lattice sort of technique. And it's also, as an added benefit, more numerically stable. So you can get cases where basically the nodal error of doing your locality approximation puts your walker in a bad spot, and you get some big spike in your energy and your population goes crazy. That's not an issue with these Tmoves. Now the caveat, two caveats. So it's been observed to have a somewhat larger time step error than the locality approximation. Sort of depends on your system, but if you're using Tmoves, you want to be very careful that you're looking at this extrapolation to t equals 0. And the other thing is, in this second paper, the authors noticed that it's not necessarily size consistent. And right now, we've just got the first one implemented in QMC Pack. So you have to be very careful about going to very large systems and using Tmoves. So far, I've talked a fair amount about the mechanics of how the code is going to handle pseudopotentials. The question that everyone, of course, should be asking is what makes a good pseudopotential, right? I don't want to spend 5 million hours on calculating something with a bad Hamiltonian. So there's a paper in 1994 that kind of laid this out. You want the all-electron and the pseudo, so when you have the pseudopotential in the calculation, the one-body density matrices agreeing beyond whatever your core radius is. So typically these things don't extend to all space. After some point, you just get a Coulomb interaction back. So you want to make the natural orbitals agree beyond the core radius. Now, most pseudopotentials don't actually come from correlated calculations. Popular forms that you'll find online that we link to, so the BFD pseudopotentials, let's say, that are now contained in the QMC Pack distribution, came from very careful Hartree-Fock treatment. So you should just keep that in mind, particularly as you go to heavier elements. It's also important to have a smooth behavior of the potential at the origin. So this is something quantum chemists don't necessarily have to care about because you can take care of it in your basis set. But if we do have some sort of cusp in the potential at the origin, that could be a problem for evaluating, let's say, your kinetic energy or your potential energy. You need to get a cancellation. So we prefer to have that to be smooth. Now, a difference between, let's say, if we're going to use this in DFT or quantum Monte Carlo, is that a hard pseudopotential is not, in principle, a problem, right? I told you that the spline representation that we use for the wave functions means that no matter how fine this grid is, I'm still only going to evaluate 64 elements for any given location. So the computational cost is exactly the same, whether my plane wave cutoff was huge or whether it was very low. The place that this can come back in is if you have a really hard pseudopotential, you can end up needing more memory than you have available. And also, we need to be careful, as I sort of mentioned in solid state calculations, that you're using a Kleinman-Bylander form in your DFT calculation, but a semi-local form, so a slightly different Hamiltonian in the quantum Monte Carlo. So there's a potential mismatch you want to be careful about. So these are, in principle, things that we can do. A practical question, and you've seen a little bit of this from the labs, is what calculations can we use to say, okay, the pseudopotential was a good choice to use in my quantum Monte Carlo? Does anyone have any ideas? Sorry, could you use your microphone, please?
All electron calculations.
So of course, in the case that you can do an all-electron calculation, this should be your gold standard, right? Although you might worry that, say, your fixed node approximation would be larger for the all-electron. So there are reasons to think that the answers don't have to be the same. So let's say I keep mentioning tantalum. Let's say I want to do a calculation on tantalum. What things could I do? So of course you want to test these things. Again, these are all expensive calculations, particularly as you worry about finite size effects. We should be looking for short tests, right? Things that I can run on my workstation, let's say, and flag potential pseudopotentials for errors. So one that has been found to be pretty powerful is just look at your isolated atom and calculate ionization potentials and electron affinities. So pull an electron off, calculate the energy versus the ambient. Now we do have a fixed node approximation if we're doing this with single Slater-Jastrow trial wave function, right? Now, in principle, you could beat this down by doing a multi-determinant expansion. But if you do this single determinant wave function, we found that if the pseudopotential is good and is going to give you properties that agree with, say, your all-electron calculation, you're generally going to be within a couple of tenths of eV of the experimental ionization potential electron affinity. If you're finding you're off by an eV, that's a red flag. Next thing you can do that's still pretty cheap is calculate the binding curve of a dimer. So this was done in I think, Jaren's lab, where I calculate the binding curve of oxygen, I think in that one, and compare vibrational frequency, dissociation energy, a bond length, for instance, with, again, experiment, or if you've got correlated quantum chemistry calculations, for instance, that's a good place to start. And again, it should agree within reasonable bounds. It shouldn't be exact if we're talking about single Slater Jastrow. For instance, there was a poster looking at the beryllium dimer that showed that a single determinate wave function isn't going to give you the exact result. But again, you should be pretty close with that. So I'd recommend that anytime you're testing a new pseudopotential, you're going to an element that hasn't at least been used in a previous DMC calculation, you at least try these things. So here are the references. For the locality approximation, I haven't, I guess, updated the Tmoves to include the second paper on the variational. This is the paper on the many-body pseudopotential theory, and there's actually been a couple of follow-ups by the Cambridge group where they've implemented some many-body potentials. These are pseudopotential libraries. Now, a word of caution, if you're going to use these for a molecular calculation, everything that you need is on the website. If you're going to use these for the solid state, you have to actually generate projectors so they can be used in the Kleiman-Bylander form in Quantum Espresso with us. For BFD, that's been done, although the projectors haven't been tested. So you'll want to make sure that you don't have something like a ghost state. You'll see this very quickly in your DFT calculations. So do a few DFT calculations. If it's crazy, it's not giving you a result that's reasonable, that's a good sign that the projectors are off. And then there have been a couple of very recent papers looking at testing these pseudopotentials. Okay, does anyone have any pseudopotential questions before we move on? All right, plowing ahead. So a couple of miscellaneous topics that may be of interest to people. So the first is magnetism. So our calculations are not limited to non-magnetic systems. We don't have to have the same number of up and down electrons. However, in QMC Pack right now, everything's done in the SZ representation. So we basically label all the electrons up or down. That's how we construct our Slater determinants. So the magnetization in your calculation is typically initially derived from a mean field calculation. You can calculate things like moments on individual atoms by, say, integrating over the charge density. And your DMC can change that. But let's say we have a ferromagnetic calculation, right? The number of up and down electrons is fixed. So nothing is going to change by doing diffusion Monte Carlo as we have it implemented. So like I say, a calculation of an antiferromagnet is pretty straightforward. If you can stabilize an antiferromagnetic solution in your DFT or whatever calculation, or you have some trick that you can use, then just put that into your trial wave function. You'll almost certainly get out an antiferromagnet in DMC. Ferromagnetism does require a bit more thought. So for instance, for a given supercell size, the actual magnetizations that my primitive cell have are quantized, right? I've got to have an integer number of up electrons or down electrons. And for ferromagnetic metals, that could even change depending on the twist angle that you use. So that gives you a bit more freedom in this granularity, but you have to be thinking a little bit more. So next, there's been some really elegant work done, let's say, for reducing the fixed node error in finite calculations, right? For instance, we can use these multi-determinant expansions that we know will eventually converge. So one thing you might like to try is direct optimization of these single particle wave functions, right? We could, in principle, use VMC to change our single particle wave functions. Now, if we want to do this naively, it's a problem, right? If I have Gaussians, there may be a handful of parameters that I have to look at. There are thousands of coefficients per orbital in a plane wave representation, so that's probably not a good place to start. So you'd like to think about using a compact representation, and there are things people are working along these lines. You can also imagine using a trial wave function beyond single Slater-Jastrow. So multi-determinant is something you might want to do. This is going to converge very slowly, and it's not size consistent, meaning if I double the size of my supercell, I'm going to have not just double the number of multi-determinants to get the same sort of answer. So be careful. That's definitely a research topic. There are these backflow transformations. So David talked about the Feynman-Kax formula that can generalize the wave function. It's possible. It's often very expensive. So now you're having to change, if you're doing a one-particle move, if you don't have some sort of short cutoff, you may have to be changing all of the orbitals every time you move an electron. So again, possible but expensive. However, one thing to consider is that you can actually afford to use a more expensive wave function for two reasons sometimes. One, of course, if you need better accuracy, you have to do it. And the other is that better wave functions from the zero variance principle are going to reduce your variance. So this means that you might have to have many fewer samples with a better wave function than you had to have with a poorer one. So it's not all doom and gloom. There are some better things that come out for your calculation. So people are often interested in excitations, right? Often we'll measure something that looks like an optical property and that we'd like to compare to. Total energies are very hard for experimentalists. So the fixed node approximation does allow for this, particularly if symmetry protects you, right? So for a given excited state, you can basically have something that's orthogonal to that, and then you use the fixed node approximation to make sure you don't decay to the ground state. Now, typical particle excitations do satisfy this, although word of caution, people have found that your nodal surface for your excited state is typically not of as quite a good a quality as your nodal surface for the ground state. So you'll typically find that you've overestimated, say, a band gap by doing this. And you should also be aware that what you've done is create an exciton, right? So this is not the same thing as promoting across your band gap. You've actually bound an exciton. And that has an energetic cost. There are other methods, something like extended Koopman's theorem, or there are sort of correlation function Monte Carlo kind of tricks where you intentionally put the thing in an excited state and watch the transient, and you can extract information out of that. Although those are more advanced topics, that's certainly not typical usage. So here are the references. Does anyone have any questions about any of those topics? Speechless, all right. Yes, please.
Can you calculate exciton binding energy?
So you certainly calculated the energy of the bound exciton. You'd have to compare to something else to know what the actual exciton binding energy, I think, is, right? Because you're getting the gap plus the energy of the bound exciton. Does anyone, Paul's looking very puzzled by that. Sorry.
No, I'm not puzzled. So you can obtain the exciton binding energy, but you have to do additional diffusion Monte Carlo calculations where you're also adding and subtracting electrons. And by taking the differences, you can pull out the binding energy.
Right, so you can get the quasi-particle gap by doing the n+1, n-1 kind of calculation.
Then how's the accuracy compared to like GW?
That's an open question. So there are people, particularly for chemical systems, and there are more, who've looked at, for instance, optimizing your nodal surface for the excited state and getting a little bit better errors. The word of warning is that there's a paper that Paul is actually on, where they calculated the gap in GW, I think beta saltpeter, and also in quantum Monte Carlo. And in that case, I think both methods weren't doing all that well, but GW is doing a little bit better, and they've improved that. Is that right, Paul?
I think that's a fair summary. So there's a paper by Tiago, TIAGO, and others in JChem Phys that I'm on a few years ago. And what we did was to compute excitation energies on a range of fullerenes with GW and also fixed node division Monte Carlo. And of course, we know that these methods have got errors. What the paper doesn't say is that we didn't compare notes during the calculations because we wanted to do a clean room comparison, but basically, and to see how accurate these methods would be. And with the non-self-consistent GW, So single shot, G0, W0, GW, as is pretty commonly practiced. And also with fixed node diffusion Monte Carlo, with unoptimized excited state nodal surfaces, the errors were larger than one might have wanted, over half an EV in some cases, not the 0.1 that you might have hoped for example. And we were able to show that by doing the right form of self-consistency for GW, the accuracy could be improved. But for QMC, that's still an open question. So the optimization for excited states that's done by Philippi and co-workers will almost certainly work, because for small molecules, they beat GW, no question whatsoever. It's a convergent method for excited states. But this hasn't been demonstrated for the fullerenes yet.
So this actually, to me, brings up a very good point, and that is, even though diffusion Monte Carlo is in principle a very accurate mini-body method, this question of how accurate is it is something that you should always have in the back of your mind. You should have an answer to that for any calculation that you do. And whether this means you've looked at some other calculations that have been done and know that what you're doing is going to be accurate, or you've, say, compared to experiment on cases where it's available. But I would encourage people not to just say, I've done DMC blindly, and this is the best answer that anyone can get. All right, so that sort of concludes the pure theoretical part of this section of the lecture. I'd like to actually talk about some calculations that I've done doing QMC in practice for the solid state. So sort of leading on to this, they're kind of a soup of approximations that one makes when doing a typical DMC calculation in the solid state. So many of them can be converged, some of them cannot. Right, so some can be made arbitrarily small. For instance, I can, if I've got the computer time, I can always do a smaller time step, right? But the approaches to how to do this are not standardized. So for instance, if I'm looking at finite size effects, we can compare it to the DFT, as I was saying, or we could do twist averaging. There are different ways of doing the two-body finite size effects. There are different choices for the fixed node errors, and then the pseudopotentials are an open question. So if I want to know the answer of how accurate is my DMC calculation, the first thing is, what DMC calculation am I talking about? What recipe did you use? And this does, in fact, matter in practice. So this is an example taken from the literature, a case study on silicon. So as I compress silicon, so I can stick it in a diamond anvil cell, basically two fancy cut diamonds, put tip to tip, squish it together, and you can get enormous pressures. And it's nice because you have access. You can actually, say, do X-ray diffraction and look at the structure of the material. So from this, they know that there's a diamond phase that is the stable phase of silicon, and that it transforms to a beta 10 phase that's metallic under pressure. And you can do this calculation with your method of choice, right? I can calculate energy versus volume for the diamond phase, for the beta 10 phase, and then I do something like a Gibbs construction, and that tells me the pressure at which the material should transform. Now, again, this isn't sort of a finished answer experimentally either. There are questions about the diamond anvil cell. Are there anisotropic stresses? But we have numbers from experiment, right? Sort of 10 to 12 GPAs, and this is 10 to the 9 pascals, if you're not familiar with GPA. Now, I look at quantum Monte Carlo calculations from the literature using different choices, let's say, for all of these approximations, and we can see that they're not necessarily agreeing with each other, right? So this is a direct consequence of these approximations that we're making. Now, if we want to answer this question in general, we might like to do sort of a broad test, right? Okay, for a given material, I can say how accurate my calculation is. Let's say compared to experiment, that could be an accident. I want to use the same methodology on a bunch of different systems and see how well that does. Now, this has been done for molecular systems. For instance, the G1 test set has been calculated. The S22 has been calculated with good effect. But in solid, you have some reason to think that the answer might be different, right? Binding is different. We've got these two-body finite size effects, for instance. We'd like to construct a test that we can easily compare to measured experimental data, right? There really isn't a gold standard method beyond quantum Monte Carlo for the solid state at the moment. We don't want this to take 1 billion core hours. 1 million would be much better. So we're going to sort of try to choose something where the finite size effects will largely cancel. Well, we need to keep a handle on this. And this sort of, at the time, was only sort of just becoming possible. It used to be that if you looked at a typical paper, they had done one energy versus volume curve, which is what I ended up doing for a single material. And this was performed on one of the first petaflop computers. So the choice that was made at the time was to generate pseudopotentials using DFT and to say, I want a really good DFT pseudopotential. Now, this turns out to not be restrictive enough, but we'll come back to that. And the way we did this is we compared to all electron calculations and said, okay, for the energy versus volume, pseudopotential that I chose was good compared to the all electron. Right. And this gets us away from, this is a 2010 paper where they basically did their energy versus volume calculation and said, okay, that didn't agree with experiment. By the way, the DFT potential that we used was bad, so we'll just shift the bulk modulus and lattice constant by what DFT had. We'd like to avoid that sort of correction. Keep everything within QMC if possible. So in this case, I was pretty careful to control all of my systematic approximations as much as I could. So for sort of low pressure and high pressure, I calculated sort of convergence, let's say, with respect to the spline spacing. Also with respect to the time step in my DMC calculation. And then with respect to the number of twists, right? So it didn't have to say that everything was completely converged with the number of twists, but I wanted to have the same relative errors at high pressure and low pressure so that my energy versus volume curve would come out accurately. And once this was done, did calculations on a bunch of different materials. At the time, this was, I think, the largest set of energy versus volume curves in DMC with the same methodology. And then sort of compared, okay, how does the equilibrium density or bulk modulus or something like that compare to experiment for these different types of binding? So the answer was the lattice constants were generally within about 1%. Bulk modulus spanning 3 orders of magnitude were pretty good. The mean absolute error, about 3 GPa, okay, on a quantity that can be between 1 and 1,000. And the RMS error about 0.6. Now, of course, these are nice absolute numbers, but what we probably care about is how well am I doing compared to something cheaper like DFT. So here it's a little bit of a busy graph, but I've plotted for each one of these materials the percent error of the DMC, which are these red dots, compared to experiment, and various other DFT functionals I might be tempted to use. So LDA, GGA type functionals, hybrids, van der Waals sort of functionals. And it's a soup, right? So the answer wasn't that my DMC is uniformly accurate everywhere and is the best result compared to experiment. And nor is it that the DMC is the worst, right? It's sort of comparable to the best functionals. And keep in mind also that for van der Waals, you know, things like a hybrid functional may not actually give you such great results. So when I compared to these pretty good van der Waals, including DFT functionals, the results were kind of comparable. So that's a somewhat encouraging result, although the DFT is obviously a lot cheaper. We'd like to do better. So that said, taking a step backward, okay, let's just say I've got the computer power and I'm going to run with those sort of errors. How well will I do for the quantities that I care about? So I used the same methodology, went back to that silicon problem, and calculated the diamond to beta 10 transition. And I got a transition pressure that's sort of 5 to 8 GPa, quite a few percent too large in this case. And the equilibrium properties are worse than what's been reported by other groups. So this, right off the bat, is saying this is probably not the best sort of systematic methodology one can choose. My equilibrium density is off by a couple percent, and the bulk modulus of this ambient phase is too large. So I had a hunch that the biggest problem in this case wasn't the nodal surface, which is what we often jump to when we think this is the fundamental approximation in diffusion Monte Carlo. I thought it was the pseudopotential error. And so I'd like to test this. So I went to a simpler system. I couldn't do, as you suggest, all electron calculations for silicon. That proved to be too expensive. But for beryllium, this is possible, right? 4 electrons. So I calculated a property. Unfortunately, this isn't known experimentally, but theoretically, there are all these calculations for a phase transition in beryllium at high pressure from the hexagonal close pack to the BCC phase. And this is a really very sensitive problem to look at. So if I imagine what sort of errors might come into this, the simplest thing I can imagine is that for one of the phases, I get a rigid shift in the energy. Let's say for that binding, it's just a little bit too high. Now, if I looked at the size of that shift in millivolts, in this case, I think I was shifting the beta 10 phase, the diamond phase. No, beta 10. And then what happens to the transition pressure? Now, this axis over here is in millions of atmospheres, right? So if I make an error of 10 millivolts per beryllium, which is not terribly large, I've shifted my transition pressure by over 1 million atmospheres. So it's a very sensitive place to look at this. And the chemical accuracy, the 1 kcal per mole, which I think is about 13 millivolts, is not good enough for this system. So early diffusion Monte Carlo calculations using the methodology from that paper yield results that I considered to be somewhat disappointing. So what I'm showing over here are the ambient phase where we can compare to experiment for things like the density and bulk modulus. And you can see we're off by quite a bit for the volume, which is the inverse of the density, and the bulk modulus. And you get a transition pressure that's almost double what the DFT calculated. Now, this isn't to say that it's wrong. It's just a little bit eye-opening given that we can see those errors. Now, if I go on and I do a calculation all-electron, which I can do in this case, you see that the all-electron numbers for the ambient phase are now in close agreement with experiment with pretty small error bars. So I think this is pretty good evidence, in the case of beryllium at least, that having a good pseudopotential is a much bigger problem than worrying about your nodal surface for these highly symmetric solid calculations. Now, in light of this, we'd like to sort of revise our recipe, right? We'd like to say, okay, how can I generate pseudopotentials that would do better? We can't do all electron calculations for heavy things. So still like the idea of using DFT-based pseudopotentials because we're going to generate our trial wave functions probably from DFT. We don't want things to be crazy. One obvious place to look is that the pseudopotentials from that paper had very large non-local channels. So I mentioned the locality approximation. That is an additional thing that we're adding on top. Maybe that's what the problem was. So in the construction, we can say, okay, let's do things that don't have large non-local channels. It's a bit harder, but can it be done? Still want to run in a DFT code. And we'll choose the core valence separation based on the energy still, right? So if there's a large gap between a semi-core state and a valence state, we'll put that in the core. Now doing this and then running a cold curve, let's say, compared to platinum, we also have small molecules. Things look pretty good. So maybe we're on the right path, right? But some elements seem to be more difficult than others. I tried the same procedure for silver, and the results weren't necessarily as good. Particularly this density was a little bit concerning. The density was off by 7%. But some parts of the construction were good. The variance of the energy and the time step error were very small because I reduced the size of the non-local channels. So it's at least one piece along the way. Now, one thing that we definitely should look at and that other people are starting to do, I mentioned these 2016 papers, is perhaps just an energy separation isn't good enough. Perhaps we need to look at the spatial extent of the core wave functions or semi-core wave functions in terms of deciding whether something should be core or valence. So this is an example from one of those 2016 papers by Krogel et al. So this was Jaron who gave the labs earlier and I think has had to leave. Looking at the ionization potential of 3D transition metal ions within quantum Monte Carlo using a DFT sort of construction. Now, one big difference between what I did is he kept all the semi-core electrons in the valence. These have, 10, I guess up to probably 20 electrons in the valence. But you can see he was able to achieve pretty good ionization potentials, and this is carried on. People have used them in the solid state. So there is definitely some hope for using DFT-based pseudopotentials in the future. So with that, finishing up a little bit early, but I hope what you've gotten out of this lecture is the differences between doing one of these calculations in the condensed phase versus a molecular or a finite system, nanosystem, how finite size effects arise and the choices that we have to mitigate them, how the wave function is represented in the solid state, and specifically how that's going to affect your run, which means what happens when I don't have enough memory on my node? How do I deal with that? The origin and testing of pseudopotentials for quantum Monte Carlo, and then a little bit of an idea of how full stack of calculations run. So this would be a great time if you don't feel like you're an expert on one of those to ask some questions.